Okay, electrolytic cell. In electrolytic cell, the energy change is from electrical energy to what? Chemical, electrical to electrical energy to chemical energy. Chemical energy. So we all know this one. It's a cell in which electrical energy changes to chemical energy is electrolytic cell. So the reactions are not spontaneous. That is the reason why we are using a battery to start the reaction. Okay, so in electrolytic cell, you know, anode. These are the general things. Okay, anode is positive and cathode is negative. Okay, so in a battery, if it's a cell, right? So this is positive and this is negative, so you have to check which side is connected to what, and then you take it in that way. And always at anode, what type of reaction is taking place is oxidation, and at cathode is always reduction. Okay, and then the electrons are always flowing from, electrons flow from always from what? Anode to cathode. There is no change in that way, no anode to cathode. Okay, right. So yeah, and then we always use a DC source. We don't use an AC source, because if it is an AC, you know how AC is, ne? First half it's positive, second half is negative, like that. So we want to keep anode as always positive, we want to keep a cathode as always negative. So to maintain the polarity of the electrode, we have to use a DC source. Always we use what? DC source. Yeah, I think these are the general explanation about electrolytic cell. So in electrolytic cell, we have 4 applications. The first application is decomposition of copper chloride. Decomposition of copper chloride. So this is the first one. Okay, copper chloride. So decomposition means splitting copper chloride into copper and chlorine. That is decomposition reaction. So for this, our experimental setup is, let me draw it for you. So now this is the experimental setup. You can see that. So we have a cell, right, with 2 electrodes are there, and these electrodes are made up of carbon. Very important. Okay, why carbon? Because it is an inert substance, it won't react with anything, so that's why we use carbon electrode. Then we connect this electrode to positive side. That means this is our anode and this is our cathode, because it is connected to positive and negative. And then the solution is copper chloride solution. If it's a solution, this copper and chlorine exist as ions. So we have Cu2 plus ions and Cl minus ions. So when you connect it, now I'm going to explain the working. When you connect the electrodes to the cell, right, what will happen is, this is positive, right? Positive will attract the negative. Okay, and negative will attract the positive, because we are using a carbon electrode, it won't react. So what will happen is, at anode, okay, our chlorine will undergo what? Oxidation. Okay, chlorine will undergo oxidation. You can actually use your table 4b to write the oxidation reaction. It is not to find out anything else. Just for writing the oxidation reaction, you can actually make use of your table 4b if you want. Okay, so if that is the case, now maybe I'll also show you. Okay, so this is table 4b. It's too small, but I'm just giving an idea. To write chlorine, you see, you can see the chlorine. You can see the chlorine reaction here. You can use your table 4b. Okay, so this is the chlorine one. So chlorine is undergoing oxidation. So when you write oxidation, you write from right to left. Okay, so you say 2Cl minus changes to Cl2 gas plus what? 2 electrons. So that means at anode you will see bubbles, and that bubbles represents the chlorine gas. Now at cathode, what will happen? Okay, so at cathode, you can see Cu2 plus is the one that is here, right? That undergoes reduction. So if you look at our copper, I told you which copper to take, ne? It's the one with 0.34 always. Okay, so you are going to write from left to right. So at cathode, the reaction is taking place, reduction of the copper. So we write it as Cu2 plus 2 electron gives what? Cu. Okay, so this is the copper that we are getting. So what will happen is this copper is going to deposit, means there will be a color change for this electrode. So carbon is normally black in color, copper is like a brownish, yeah. So you can see that at the end of the reaction, you will see that this cathode is changing the color. That means there will be an increase in its mass. So this is what you need to know from decomposition of copper chloride. Second application is refining of copper. So when you are refining copper, you have impure copper, right? When you are digging it from the surface of the earth, you are getting impure copper. Okay, so when you are drawing the electrolytic cell, that represents the refining of copper, right? Your anode, okay, your anode must be the impure copper all the time. I'm just drawing it to show you that it's something different. Your anode is supposed to be what? The mm, yeah, anode is supposed to be the impure copper, and cathode is supposed to be what? A piece of pure copper, a thin pure copper. Okay, thin layer. So this one is pure copper, and this one is what? Impure copper. And the solution must be a solution of any copper solution, right? So normally we use copper sulfate, CuSO4. Also you can use copper chloride. So when it is copper chloride, they will always mix this question with the first one is the decomposition of copper chloride. Okay, so we have, in copper sulfate means we have copper ions, and if it is sulfate, we have sulfate ions. If it's chlorine, you have chloride ions. So I'm just writing copper Cu2 plus ions only. Okay, now what is going to happen here is, when you are connecting it to the cell, right? Now oxidation and reduction will take place. At anode, oxidation, because this is our anode, right? At anode, oxidation is taking place. Okay, now it's an impure copper. Impure copper means it has impurities. We have copper in it here. Also we have silver, we have gold, we have platinum. Usually these are the three impurities. Sometimes we do have zinc or any other substance, but usual impurities are gold, silver and platinum. Out of these, so our copper is this one. You still remember the copper that I told you, right? So copper, gold, silver, platinum, it must undergo oxidation. What is happening at anode is oxidation, right? But when you look at silver, you see this is silver, this is platinum. Hmm? So when you look at copper with silver and platinum, copper is a stronger reducing agent than silver and platinum. Gold is not there, but gold is also between, I think it's below silver. Okay, right. So you can see that out of these four that I stated now, copper is the only one that undergoes what? Oxidation. Okay, so copper will undergo oxidation. So you write copper changes to Cu2 plus 2 electrons. Okay, so what will happen now with the impurities? Impurities will slowly deposit. It will detach from, as copper is coming out, you can see the size will decrease, right? So what will happen is these impurities will detach it from the anode, and it will deposit at the bottom of the container, and then it will be removed and separated in using different other methods. Okay, because they are called sludge. You remember that the impurities, we call them as what? Sludge. Okay, so if you want to find out whether an impurity is part of a sludge, so it must be below copper. It must be below what? Copper. Okay, if it's below copper, that's sludge. For example, if they say let's say nickel, right? So you see nickel is here, ne? Nickel is not part of a sludge. Sludge means it must be below copper. Okay, you understand that way, right? Okay, and then that's one method. You can use it for identifying whether it's a sludge or not. So this is happening at anode. So now each time the oxidation is taking place, the copper ions will come into the solution, and then that will move towards what? The negative electrode, which is the cathode. So at cathode, this copper ion will undergo reduction. So you write the same reaction from left to right. So which is Cu2 plus 2 electron gives Cu. That is the cathode reaction. Okay, right. So that means the size of the anode will decrease and size of the cathode will increase. Okay, so you will get pure copper from refining of this copper. And then also the concentration of the solution, you see that the concentration of solution will not change, because you can see every time there is an oxidation taking place, one copper will come out, isn't it so? At that same time, that copper will move out. So what will happen to the Cu2 plus in here? That number will not change. So the reason why the concentration is not changing, we say the rate of oxidation is equal to the rate of reduction. So that is the point you need to explain. So that is what you can understand from refining of copper. And remember, if they are using copper chloride as the electrolyte, always remember, how do you see that it's refining or decomposition? In decomposition, the electrodes are made up of carbon. But in refining of copper, the electrodes are, anode is impure copper and cathode is pure copper. Okay, the third application is electroplating. So in your syllabus, they specified electroplating of silver. Okay, silver spoon, something like that. Okay, but basically it's silver. But like I explained in class, that they also ask for other substances. So the idea is going to be the same. You have anode and cathode. You see, when you look at our cathode, you see I connected the other way around for you to see, right? So the negative is our cathode. So always the cathode is the substance that you want to plate. Okay, if it's a ring, it's a ring. If it's a spoon, it's a spoon. So whatever the substance that you want to plate, that must be your cathode. And the metal that you are going to plate on, that means that is your anode. So if you are plating silver on this ring, then this anode must be made up of silver. Okay, and then the electrolyte must be a solution of silver. So usually if it's silver, we use silver nitrate, AgNO3. So that means we have Ag plus and NO3 minus in the solution. Okay, so when you connect it to the cell, what will happen? Anode undergoes oxidation and the cathode undergoes reduction. Look at our anode. Anode is silver. Okay, when you look at your table 4b, I didn't attach here. When you look at table 4b, we have silver reaction. Like I'm just writing the whole reaction as it is in Ag plus plus 1 electron gives Ag. This is the reaction in your table 4b, right? So at anode, it's oxidation. Oxidation means you write from right to left. So at anode, Ag is changing to what? Ag plus 1 electron. Okay, so the Ag plus will come into the solution, right? From the solution, the Ag plus is moving towards what? The negative electrode, which is our ring. Okay, there it undergoes what? Reduction. So at cathode, what is happening is reduction, right? So the same reaction, you can see you are writing from left to right. Ag plus 1 electron gives what? Ag. So that means you are now going to plate with what? Ag on the ring. So this is how we can explain the electroplating. Here also the concentration of our electrolyte will not change. So what is your reasoning here? You can see when one Ag plus moves into the solution, one moves out of the solution, right? That's what is happening here, right? So uh, um, it means the rate of oxidation is same as what? Rate of reduction. So that is why the concentration of this electrolyte remains the same. So this is how basically electroplating is. So if you are plating with any other substance, okay, so here the same theory we are applying there. That substance must be the anode, okay, and the object that you want to plate, that object must be the cathode. Now what are you plating with? If you are plating with nickel, anode must be nickel. If you are plating with copper, anode must be copper. If you are plating with gold, anode must be gold. And the solution must be a nitrate or chloride or sulfate of these what these metals like silver nitrate, we can say gold nitrate, or gold chloride or something that we can use it, but it must be an electrolyte of the same metal. And then you write the same reaction from right to left and left to right as the anode and cathode reaction. Okay, right. And I always remember the concentration of the electrolyte always remains the same, right? Why? It is because the electrolyte is same, because the rate of oxidation is same as the rate of reduction. Okay. The last application is electrolysis of concentrated sodium chloride solution. So if you look at concentrated sodium chloride solution, the electrodes, you can see these two electrodes, they are also made up of carbon. Okay, these are two carbon. We saw carbon electrode for decomposition of copper chloride. So the next one that has carbon is electrolysis of concentrated sodium chloride solution. Okay, and since I connected this to the positive, this is our anode and this is our cathode. Okay, and then our solution is concentrated sodium chloride solution, concentrated NaCl solution. So in the solution you have Na plus, Cl minus and H2O. Okay, because it is concentrated sodium chloride solution, so that is why we have Na plus, Cl minus and H2O. Right, so when you connect it to the cell, you see anode is positive. Positive will attract, because carbon electrodes are there, they won't react. So from the solution, the chlorine will move towards what? The anode, because anode is positive, right? So I showed you in the table 4b where is chlorine. Then you can actually copy that as the anode reaction. At anode, oxidation of chlorine ion, right? So oxidation, and the reaction is 2Cl minus changes to what? Cl2 plus 2 electrons. Cl2 is a gas, okay? 2 electrons. That means from the anode you will see the bubbles moving up, and that bubbles represents Cl2 gas. Clear? Now after Cl minus, now what do we have in the beaker? You have Na plus and H2O. So one will undergo, between these two, one will undergo what? Reduction, and that is taking place at cathode, that is reduction. Now to decide what will undergo reduction, we are going to use our table 4b. When you look at the table, you can see this is Na plus and this is H2O. You see, these are the two. Right. So when you compare Na plus and H2O, right, First one is always undergoing oxidation and second one is always undergoing reduction. So I can say H2O is a stronger oxidizing agent than Na plus. So what will undergo reduction is H2O. So our cathode reaction is going to be this one. You write from left to right, which is 2H2O plus 2 electron gives what? H2 gas plus 2OH minus. That means from the cathode also you will see the gas going out. And what gas is it? Hydrogen gas. So you can see from anode there is gas, cathode also we will get gas. At anode is chlorine gas and at cathode is hydrogen gas. Along with hydrogen, we are also getting OH minus. So that OH minus will be in the solution, right? These two will now combine and we will get what? NaOH. So in this application, you can see we are getting three things. We are getting chlorine gas, we are getting hydrogen gas, and we are getting what? Sodium hydroxide. And in this reaction, when since sodium chloride is forming, the solution is always alkaline or basic solution. This is also a common question. Why it is the solution alkaline or acid? It's alkaline. Why? Because of the presence of either you say OH minus or because of NaOH. Okay, so that is how you can explain the electrolysis of concentrated sodium chloride solution. Okay, so you need to study this, and then you will see that you are answering the same thing. You don't see anything different from here. Okay. Now, also with, so these are the four applications. Also with this application level question, nowadays they also ask what the calculations, right? So to get the calculations to be done, I'm just giving you some idea here. We are going to use I is equal to Q over delta T. N is equal to Q over E, right? These are from physics. From chemistry, we going to use N is equal to sometimes V over Vm, right? Sometimes it's N over Na, right? Then sometimes we use N is equal to mass over molar mass. Okay. So these are the equations we are going to make use for the calculations. Okay. So for example, let's say they gave us the volume of like in this case you can see at anode we have chlorine gas produced and at cathode we have hydrogen gas produced. Okay, so let's say we are getting hydrogen gas at cathode and they are saying the volume of the hydrogen gas is just say 250 cm cube for example. Okay, and then if cm cube means you change it to dm cube, 25 dm cube. And they also say that the molar volume means vm will be given, which is let's say 25. I'm just giving an example, okay, or 24 whatsoever, right? So we need to calculate the number of electrons produced, for example, if that is the case. So in this case, you see, when you have V and Vm, you can calculate the number of moles, okay? Number of moles of hydrogen using V over Vm. And then you must look at your table. You can see this is the hydrogen one, right? Hydrogen gas. So you must look at the reaction between hydrogen gas and the electron, okay? The ratio is 1:2. So once you get the number of moles of hydrogen gas, we can calculate the number of moles of electrons using the ratio. Okay, so I said 1:2. So you will get what? Number of moles of electrons. Once we get number of moles of electrons, then you will calculate the number of electrons transferred using N is equal to N over Na. So this N is the number of moles of electrons. So then capital N represents what? Number of electrons. So if they are looking for number of electrons, we can stop here. Okay. Now, if they are looking for maybe current, then from here you go to this equation. Okay, because in physics this also represents what? Number of electrons. So in physics it's small letter n, but in chemistry it's capital N. So using this n, E is a constant, 1,6 times 10 to the power of minus 19. You can calculate what? Charge. Once you get charge, we can calculate current because time will be given. Then you use I is equal to Q over delta T to calculate the current. So this is the basic idea for doing a calculation. Sometimes they do ask for mass, or sometimes they will give you mass. Okay, so that means using mass you will calculate the number of moles. You see, the same way that we did here, né? Number of moles of that given substance. Okay, and then you take the ratio of number of moles with electrons, and then usually we go for number of electrons, and then if it is only for number of electrons we can stop there, or from the number of electrons you go for the charge, from the charge you go for current. Sometimes they do the other way around, like they can give you the current, okay, and the time. That means we are going the opposite way now. So using I and delta T, you will calculate first Q. Then using Q, you will calculate the number of electrons. Then from there, using the number of electrons, you can calculate the number of moles of electrons. Then take the ratio to get the number of moles of that substance. If it's only for number of moles, we can stop there. Or if it is for mass, from the number of moles, you go for mass. You see, we are playing around with these equations. Okay, so I hope this will help you. Thank you.